Hey everybody, this is Victoria and Corey, and we are the Professor Stu Boys. Welcome back to the Professor Stu Boys channel, and today we're going to be talking about effective nuclear charge and the trends of the periodic table that follow this effective nuclear charge.
All right, so first let's just think about nuclear charge. What we mean by nuclear charge, and this is often represented by the letter Z, a capital Z. This is simply the number of protons. This makes sense. The nuclear, like the nucleus, the charge in the nucleus, it's related to the number of protons. Well, we represent the effective nuclear charge with a little Z asterisk. We call it Z star. Just sounds kind of cool. But this is the net charge experienced by an electron when there's, well, by an electron in an atom. And let's take a look at a picture that I think will make a lot more sense.
All right, so we're going to be looking at this picture down here. So we have the nucleus in the center, and that's where all of our positive charge is. So there's our actual nuclear charge. As n increases, so as we get further and further away from the nucleus, the outermost electron will have less of an attractive force pulling on it from that nucleus. And the reason is because it experiences shielding of the other electrons that are in between it and the nucleus. So you can see the blue arrow that is here. So we have a blue arrow that's saying what the actual draw is from that nucleus to that electron, just Coulomb's law, opposites attract. But we also have these other negative electrons in between, and that's repelling that outermost electron. And it's kind of getting in the way of the nucleus being able to hold that electron as tightly as it would have if we didn't have any of the shielding. We call this shielding in between the outermost electron, or the electron that we're talking about, and the nucleus.
So there's really two things happening here. Like as the n gets bigger, or as we get more electrons, the distance is further, so that that attraction would be weaker even without the shielding electrons. But in addition to this, we've got all these shielding electrons in between the nucleus and the outermost electron. So the effective nuclear charge can really go down quick.
So we have, as you go down the periodic table, n is increasing, right? So we have shells. As we go down the periodic table, we're getting more and more shielding, less pull from the nucleus. But as we go across a row, think about this. So as we add electrons to an additional, okay, I want to start here. So as we go across the periodic table this way, we're adding electrons. So you'd think, okay, we're having more shielding, but we're also adding more protons. So our proton is getting stronger, our nucleus is getting stronger, and it's holding those electrons. And the electrons are, additional electrons are being added to the same shell. So if I add another electron here, my nucleus is getting one, stronger by one proton as we're moving across from left to right. But the electrons that we're adding are not adding very much additional shielding. So our effective nuclear charge is getting stronger as we're going from left to right, and it's getting weaker as we're going from top to bottom as we progress around the periodic table.
So let's just draw that on this periodic table. Like what is the trend for effective nuclear charge? We know as we go down a group, it gets less because it is the distance, the extra electrons. And we know if we move left to right, the nuclear charge actually gets greater because we are adding protons. So you can see, like, we could put this in terms of two arrows, like increasing effective nuclear charge increases as we move from the bottom up, and also as we move left to right. Well, we could represent that with just a diagonal arrow as well. We could say, the lowest effective nuclear charge is going to be in the bottom left, and the highest is going to be more toward the upper right. Now, these are just trends. There are exceptions, but this is the general trend for effective nuclear charge. So how can we relate this to the size of an atom? Just think about this for a second. Well, we know that they're going to get bigger if we have more energy levels. So if we move down a group or a family, the size is going to get much bigger. This is intuitive. But moving left to right, this is like the effective nuclear charge. It's not quite as intuitive. You would think, we're adding electrons, it would get bigger, right? But it really doesn't. And the reason is these added electrons are going into the same subshell, and the addition of the protons is more has more of a contribution. Those extra protons are able to pull those electrons in closer. So again, just a trend. It's not exact.
So largest down here in this corner and smallest in the upper right. All right, so what trend would we expect for metallic character? So what is a metal? A metal loses electrons. So metallic character is, what's the tendency to lose that electron? How easily can that electron be lost? So when we're going down the periodic table, we're getting larger and larger, and the potential energy is getting larger and larger, and the electron is being held much more loosely in these larger atoms. So the ability to lose that outermost electron is easiest at the bottom of the periodic table than the top.
Another way, just an easy way to kind of remember this is we know that the metals are on the left-hand side of the periodic table.
Right.
And so we know that the metallic character has got to be favored on the left, but the lower left is going to be the most metallic. So this is inversely proportional to the effective nuclear charge. So as the nuclear charge is weaker, we're going to see more metal-like character, more ability to lose electrons.
All right, so electron affinity. Electron affinity is the amount of energy that's released to form a negative ion. And this kind of can be thought of as how easy or how much pull does it have to attract an electron to it to make a negative ion. So how strong it is. So since energy is released, this electron affinity is actually a negative number. So an increased electron affinity is actually a larger negative number, but it also trends with Z star. So as we have a higher affinity for the electron, as the electrons are being held tighter, Z star is higher, your electron affinity would be greater, right? So it's pulling those electrons stronger. It's able to then even take an extra electron and hold it as well. So it trends with Z star. So we have increased electron affinity going, which way is that?
Left to right and bottom to top. Or we could just put the diagonal in there to represent the general trend. So we can use the periodic table to compare elements for size, electron affinity, numerous things.
That one other thing for the electron affinity that excludes the noble gases. So the noble gases are very content with themselves. They don't want to be a negative ion.
Yeah, I think the noble gases don't really follow any of these trends, but there's definitely a general trend. So what would we expect for ionization energy? Ionization energy is the amount of energy required to remove the outermost electron. So to form an ion. So it's logical that if that outermost electron was a long, long way away from the nucleus, then it wouldn't take much energy, and this is true. So this also trends with effective nuclear charge in that going from the bottom to the top of the periodic table, the ionization energy increases, and moving left to right, it increases. So over there, that upper right, the fluorine has relatively large number of protons in the nucleus, and it just has the 2s2p for the valence shell. They're pretty close. It's got a nice tight grip, high effective nuclear charge. So do you want to draw that ionization energy trend as a diagonal? Here we go.
Again, ignore the noble gases for that. Okay, so we have more than one ionization energy. So the first ionization energy is the energy required to remove the first electron, or the most energetic, the outermost electron. And the second ionization energy is to remove the second electron, and so on. The second ionization energy is always larger than the first, so it'll pick off the easiest one first. So the lowest energy required electron will take off first, and then it would take off the second. However, it's interesting to note that the ionization energy is extremely large once the atom reaches a noble gas configuration. So if sodium loses its one outer electron, it now has the electron configuration of the previous noble gas. And it will be very, very, very difficult to remove the second electron. So there would be a large difference between the first ionization energy and the second ionization energy for that first group, because it has one electron in its outer shell. The second group has 2 electrons in its outer shell, so it would have a very large difference between its second ionization energy. Once it loses those 2 electrons, it's like a noble gas configuration. The third ionization energy is really high because that noble gas configuration will not want to lose that electron. So that third ionization energy would be very high for group 2 elements. So here's a summary.
Yeah, this is just basically the summary. You know, we can think of these trends associated with this effective nuclear charge concept, and terms like electron affinity. I like technically this is an amount of energy that's released, but I like to think of it in terms of how badly the element would want that electron. So fluorine is going to really want an electron to fill that outer shell. Ionization energy, is another one. It trends directly this way. A lot of energy to remove an electron from fluorine. There's a term called electronegativity. We haven't really introduced that one yet, but it's actually kind of a hybrid term that is kind of like electron affinity and ionization energy. The scale's a little easier to manipulate, but we'll get to that shortly. And we have some things that trend indirectly or inversely with this effective nuclear charge, and that's atomic size. So our largest atoms are down in the bottom left, and metallic character.
So here's some practice for you. Arrange these elements, lithium, potassium, and oxygen, in order of increasing. So put all of them in increasing order for these different characteristics.
This is a typical type question that you might be asked.
Right, so you should be able to compare anything in a group and anything in a period as well. Pause the video and give it a try. All right, here's your answers. Again, you want to use the comparison of within the group and then within the period.
And it might be worth just pointing out that little symbol there that, so that atomic size, it's saying that the oxygen is less than, that's the less than sign, less than lithium, less than potassium. So they are in order, increasing order.
All right, so this concludes our trends of the periodic table. We want to just let you know and just kind of remind you that there are exceptions to these. This is just the basic trends that you may see some, and there are some reasons for some of the exceptions, and we might get into that in some future lectures. But just know that there are some exceptions to these trends, but this is the general trend, and the Z star is the reason for them.
All right, thanks for watching.
Bye-bye.